Let me tell you a few things about the course, which is probably clear from the content of the course. It's going to give you a bird's eye view of a lot of topics in physics that are of interest, that are of contemporary interest, and that one should learn in order to learn physics. So, we have talked about classical mechanics earlier and have given you very brief introduction to Newtonian mechanics and then Lagrangian mechanics, and then we have talked about classical relativity or the special theory of relativity mainly, in which we talked about time dilation and length contraction. However, in no way these topics that have been taught are complete. They need to be supplemented by a lot of readings and solving a lot of problems. A few of them, or rather a part of those requirements, will be served in the assignments, but then you should do also reading other than that, because the scope that I could cover a large part of any of these topics is limited. Okay. So, with that introduction, let me go on to quantum mechanics or these quantum ideas, and we talk about atomic structure. So, let me give you a brief introduction of quantum mechanics or how it starts. So, many of the known concepts of classical mechanics have to be revised, or even some of them had to be discarded to build quantum physics. And we are slowly getting into the realm of microscopic particles, for example, atoms, electrons, protons, photons, etc. And these signatures of these particles, that is subatomic particles, atomic particles, and broadly they would be called as quantum mechanical particles. They are realized through the discrete energy levels, or sometimes we see intensities such as that is seen in mass spectrograph and so on. But they can also be visualized, that is, these particles can also be visualized in high resolution microscopes, for example, high resolution transmission microscopy or scanning electron microscopy, which are known as SEM, TEM, or even field emission scanning electron microscopy called as a FESEM. So, we will not talk about these experiments, but it is in your interest that you should know how signatures of these subatomic particles are are seen or can be realized. So, let me ask a few questions. So, is quantization a proprietary property of quantum mechanics, like the quantization of the energy levels or quantization of the angular momentum? And the answer is no, because the frequencies of the organ pipes that you are aware of are quantized as well. Now, this simply stems from the fact that when you are trying to solve a differential equation pertaining to certain boundary conditions or initial conditions, you would get quantization. For example, these open organ pipes, the frequencies are quantized in V over 2L. And in closed organ pipes, the frequencies are quantized in unit of V over 4L. So, V over 2L and V over 4L, which means, say let us talk about a closed organ pipe closed at both ends, and they have frequencies which are V by 4L and 3V by 4L, which means that there is no frequency that is possible. So, the first harmonic comes at 3V over 4L. Between the fundamental frequency and the first harmonic, there is no frequency that is available or that can be generated, and this purely from the fact that you are solving a wave equation. Here we are talking about sound wave. So, wave equations pertaining to boundary conditions that are they are closed. So, they have to have nodes at the extremities or at the boundaries. So, one gets quantization there, but what is a speciality of this quantization that we are going to see in quantum mechanics? The speciality is that the quantization, it carries a scale of the Planck's constant, which we write as either h or h cross. So, this is something new, that all these other things that you have talked about, just like what we have talked about the frequencies of these organ pipes, they are not quantized in the scale of H or H cross. Remember that H or H cross, they have a dimension of the angular momentum. So, H cross is H over 2 pi. So, it is simply just a factor that divides. So, we will use them interchangeably with this factor of 2 pi at times. So, is there any other similarity or dissimilarity between the classical and the quantum physics? And the answer is that the superposition principle. Once again, this is due to solving the linear differential equation. We would be talking about mainly in quantum mechanics, the second order linear differential equation. And when we talk about linear differential equation, there is no term such as x and y, or there is no term which is a product of the two variables, or rather the dependent and the independent variable, and so on. So, there in these linear differential equations, these superposition principle works, and we can talk about Laplace's equation in electromagnetics, where we solve these equations pertaining to certain boundary conditions. And in a similar spirit, we will be talking about solution of Schrodinger equation in certain kind of potential. Both have a nature that's similar. As I said, it's a second order linear differential equation. And if say psi 1 and psi 2, or y 1 and y 2 are solutions of these equations, this psi is just a function of x, and say y is also a function of x, then a C 1 psi 1 plus a C 2 psi 2 is also a solution, and this is called as a linear superposition. This holds in this quantum mechanics, or rather solution of Schrodinger equation, and also holds in classical electromagnetism. Now, while talking about relativity, we have seen that the non-relativistic or the Newtonian mechanics that we have learned in a nutshell is really a limiting case of relativistic mechanics, and valid for V much smaller than C. And so, if V becomes of the order of C, or at least 1/10 of that or 1/100th of that, you need to go to the relativistic mechanics, because the space and time would be coupled there, and you have all these length and time, they would not look the same as they would look in a stationary frame. Okay. So, similarly, this classical mechanics is also a limiting case of quantum mechanics. Okay. So, just like relativistic mechanics should be the description of all particles moving with any velocity, I mean, which could be velocity of close to velocity of light, or it could be much smaller than the velocity of light. In fact, there is a problem with Newtonian mechanics that it does not give any special consideration to the speed of light, and that is why it fails, or rather it is an inappropriate description, which is what we have seen. Similarly, classical mechanics also works in certain domain, and quantum mechanics is should be universally applied to all particles to decipher the properties of these systems, microscopic or macroscopic. However, for macroscopic particles or macroscopic bodies, classical mechanics works fine, and this is what we have learned. So, classical mechanics is a limiting case of quantum mechanics. Okay. Classical mechanics provides description of macroscopic bodies only, which is what I have said. Quantum mechanics is in principle applicable to microscopic objects, but there is no embargo on quantum mechanics to to describe even macroscopic bodies as well. So, there is also a difference in quantum mechanics for this case when V is of the order of C and V is much smaller than C. See, the velocity of a particle, V is the velocity of a particle. Velocity of a particle can never be larger than C, but it can be of that order, means that 10% of that C is also very large velocity, knowing the speed of light, which has been talked about many a times while teaching relativity. So, these are the cases that also have to be discerned, or they have to be distinguished even in quantum mechanics. Okay. So, here I present a table. The table has 4 quadrants, and the ultimate description is in the first quadrant, that is on the left top, which I wrote as relativistic quantum mechanics, and on the right top there is non-relativistic quantum mechanics, which is what we are going to talk about now. At the bottom right is the non-relativistic classical mechanics, is the Newtonian mechanics and Lagrangian mechanics that we have learned, and relativistic classical mechanics is what we have learned earlier, that is in the last module we have learned that. So, this has been done little, again this has been done in short. This is what we are going to do now, and the one that is on the first quadrant would be stored for a later use. Okay. So, let me go into the atomic structure. Okay. And while talking about atomic structure, there are many theories that have stemmed from very early on, and now we know that what the structure of the atom is, but it is important to know about the history and the way it developed. So, there are these Dalton's atomic theory, Thomson's model, and then Rutherford model, Bohr's model, and then the quantum mechanical ideas, which gives rise to the wave particle duality. And we will not talk about Dalton's atomic theory or Thomson's model, but we will talk about the Rutherford experiment of backscattering by the alpha particles or of the alpha particles, and then we will talk about Bohr's model a little, and we will of course talk about the wave particle duality, which says that there are experiments in which the electromagnetic radiation or the photons, they show up as particles because we use the energy and momentum conservation relations, whereas in other experiments they show up as waves showing diffraction and interference, these kind of phenomena, which are again they are seen in waves for the case of waves. Okay. So, the early on let us talk about that story as well. So, the earliest concept of atomic structure was arguably given by an Indian philosopher, Maharishi Kanad, whose concept of matter constitutes of the building block which he called as Parmanu. Then the Greek philosopher Democritus also claimed that matter is formed of indivisible elements, these are called as atoms, and is credited with the early proposal of discovery of the atomic structure. Of course, now we know that atoms are the building blocks of matter, and a nucleus composed of neutrons and protons, and the electrons are orbiting around the nucleus. Electrons have negative charge, protons have equal but a positive charge, and neutrons are chargeless, though neutrons have magnetic moment which are important for certain kind of experiments. And the nucleus accounts for 99.94 of the atomic mass. This is in striking sort of similarity with our universe, where the sun occupies a similar percentage of this mass of the universe, and these planets which are they orbit around the sun in their own orbits, and they are held by the gravitational force. And here of course, that they are held by the centripetal force. So, what is Rutherford model? So, Rutherford he was around between 1871 to 1937, and most of these experiments were done in the early second decade of these 1900s. So, around 1911 or so, most of these experiments were performed, and he was assisted by Geiger and Marsden. And what they did was that they did a scattering experiment where he bombarded heavy atoms by alpha particles, which have mass 4 units. And so, these are 2He4. So, these are the bombarding particles or the projectiles. In fact, to his surprise, he found that these are like shooting bullets at say thin tissue paper or something. And to his surprise, he found that some of them actually return back along the direction in which they are fired. So, this sort of gives a feeling that there is something very strongly sort of positive, so that these alpha particles they are repelled and they return back. So, that is how he tried to visualize the structure inside an atom, and this is what the main the discovery is all about. And in that experiment, the effect of scattering by electrons is neglected, and these are really they may have some effect, but they are not taken into account. Also, there is no appreciable movement of the nucleus or the atom due to collision, and that is why he chose heavy atoms, and this is probably one of the corrections that need to be done on Rutherford scattering experiment, where you need to also talk about lighter nuclei. Okay. So, the corrections for lighter nuclei need to be accounted for, and also the relativistic corrections, which because the speed of these alpha particles is they are comparable to that of light, it is 1/20, that may be also needed to be taken into account. And so, let us try to sort of tell you what the experiment is like. So, there is a source of alpha particles that you see here, and that is shooting alpha particles at this thin gold foil, and how thin it is, it's I believe it's probably something around 500 to 600 angstrom maybe, and they are deposited in this along this ring that you see, and this ring that you see, the ash colored ring, it is actually to give you a feeling that the angular distribution of the scattered alpha particles are measured. Okay. And as you see that some of them are really reflected close to the direction, and some of them actually could be almost tracing back the direction that of the incident alpha particles. Okay. So, the scattered alpha particles are on the detector, or they are captured in the detector, which are placed in some kind of angular array, and so most of the particles are found to be undeflected. So, they go pretty much in the direction that they are fired, and there could be a little deflection, and as you see that there is a circular fluorescent screen, and whenever there is an alpha particle that impinges on the screen, there is a spot that is formed, and the spot is noted, and its angle with respect to the incident direction is noted. So, Rutherford realized that the backward scattering of the alpha particles indicate that there is a small region of positive charge which is responsible for this, and this led to the discovery that they are the protons and also the neutrons, they are there inside this positive region. So, let me show you a schematic picture of the scattering process, and we will talk a little about this scattering. It is important to want to find out that this is what Rutherford did. He actually have worked out the trajectory of this alpha particles. Okay. And so, there is this alpha particle, and this plus ZE is the nucleus. Okay. And this is 2E, but we can call it as ZE with a small z, and this is a capital Z. Okay. So, capital Z corresponds to the number of this the atomic number of the nucleus, and E is the electronic charge. And so, the alpha particles are bombarded in this direction, and they get scattered in this direction, and let us call this velocity as v prime, and maybe this as b prime as well, but we will show that v equal to v prime and b equal to b prime. And you see that there is a scattering angle, that is theta, which is measured with respect to the incident direction. And if you let us talk about another angle, which let us call it as phi, and so this is that angle, and maybe there is this, and maybe this perpendicular distance, let us call it as d by 2, all of it which we will use there in the calculation and so on. And so, this is the schematic diagram, and let us try to work out that what is the form of this trajectory, so that we have an idea that there is a small region of space which deflects all the alpha particles, and hence this should house positively charged particles, which are of course protons. Okay. So, we can show that V equal to V prime, I am writing it as a scalar quantity, and B equal to B prime. That is, now this V is of course the speed of the particle, and B is called as the distance of closest approach, that is, so this is the distance over which it can approach the the location of this nucleus. So, this is called B, and after it gets scattered and on its way to the detector, let us call that as B prime. That is it's called either called as the distance of closest approach, or it is also called as the impact parameter. And it plays an important role in in this scattering theory. Okay. So, we will prove this, that the initial and the final velocities are same, and the initial and final the impact parameters are same, and which can be understood by the conservation of angular momentum, because there is no torque that is acting, the angular momentum will be conserved. So, it is mVb equal to mv prime b prime. So, that tells us that Vb equal to V prime b prime, where m is the mass of the alpha particles. Okay. And also the kinetic energy is conserved. So, this is half m v square is equal to half m v prime square, and that tells us that V equal to V prime and B equal to B prime. Okay. So, V equal to V prime here, and then if you put it on the equation above, then it gives you a B equal to B prime. So, which means that the initial and the final velocities are same, and the impact parameters are same before collision and after collision. So, after this alpha particles collide with the nucleus, I mean they do not collide head on, but they feel the presence of the nucleus and get deviated because of this. There is a repulsion that they feel, and this also tells you that there is a positive concentration of positive charge somewhere, which is at this position, which we have shown as ZE, the nucleus. Okay. All right. So, we need to know the trajectory. So, the trajectory is needed, and how you can get the trajectory is the following. Okay. So, the force balance equation can be written. So, what the trajectory means is that the relationship between some r and phi, where r is equal to some some distance, that is it is like this kind of a distance. Or you can say that it is a b and phi, that is also equally possible to get you a trajectory that you are looking for. And the trajectory is important because we need to know how they are deflected and what are the the conditions on various parameters. That is, if it comes very close, b becomes 0, that is if it is heading towards directly towards this ZE, that is the nucleus, then it will of course be reflected back. Okay. So, how does the force balance equation look like? The force balance equation, the force is equal to nothing but equal to ZE, it is 2E, but we will write it as ZE, because these alpha particles are nothing but this 2He4. Okay. So, that is why Z is 2, but we will just keep writing it as ZE, and distinguish between the small z and capital Z, which is this the nucleus, and divided by 4 pi epsilon 0 r square, where r is the distance between the alpha particle and the nucleus, and it is a variable. I mean this r is variable, and this is a force. Okay. So, how do we write force in some generalized form? In the r phi coordinate, phi is shown there. So, it is this is equal to m, and we have this as d2 r dt2, and then it is a minus r d phi dt whole square. Okay. This is called as a radial acceleration, and this is nothing but omega, and this whole thing is called as the centripetal acceleration, basically r omega square. So, this is the this force is equal to mass into acceleration and so on, and in order to find out the trajectory, define r equal to 1 over u. So, r is inverse of u, or u is inverse of r equivalently, and this is done in even in the the gravitational case, when you want to calculate that whether the trajectory of a planet is bounded or it is it is a hyperbola which sort of escapes. So, this kind of this redefinition of this angular or rather radial variable is done as well. Okay. So, why we did that? Because we need to calculate each of these radial acceleration and the centripetal accelerations separately, and so we can write down this as dr dt. This is equal to dr d phi and a d phi dt, and so this is like a dr du du d phi and a d phi dt. Okay. And this is nothing but minus 1 over u square, because dr du is minus 1 over u square, and then we have a du d phi, and then we can write this as, so d phi dt is nothing but omega, and we can write this in terms of the angular momentum, which is equal to mvr and v equal to r omega. So, this is equal to m omega r square. So, now we need omega. So, omega is equal to L over m r square, or this is equal to L u square by m. So, we will write, in case of d phi dt, we will write L u square over m, and the u square will cancel, and we have this as minus L over m du d phi. Okay. So, that is your dr dt, but that is not where you stop at, because you need d2r dt 2. So, that is the second derivative of this. So, this is equal to d d phi of dr dt and d phi dt again, which is nothing but omega. So, this is equal to minus L over m d2u d phi 2. So, we are slowly cruising at this d2u d phi 2, that is this u is nothing but 1 over r. So, there is a relationship that is emerging between r and phi. If we can find out from this force equation an equation which gives you a trajectory, that is what we are looking for. Okay. So, this is can be simplified as L square u square by m square d2u d phi 2, and this m is nothing but the mass of the alpha particles. Okay. So, if you put 2 in 1, that is this equation, and let us define the equation that we have written here as 1. So, now we have everything, we have a d2r dt 2. So, this is dt 2, okay, and you have d phi dt, which is nothing but omega. So, we can simply put 2 in 1, and what one gets is the following. We get an equation which is L square u square by m square, and there is a d2u d phi 2 minus 1 over u L u square over m whole square equal to small z capital Z E square u by 4 pi epsilon 0 m. Okay. So, that is the equation that we get. This is just the force balance equation. Now, we have put all the radial and the this centripetal acceleration and their forms in terms of u, phi, L, etcetera. L is a constant of motion. Okay. So, we can write this as instead of defining this as 3, we can define the next one where we make a so we do a bit of simplification and write this at d2 u d phi 2 plus a u. This is equal to minus z and capital Z and this divided by 4 pi epsilon 0 L square, and we use this impact parameter L, writing it in terms of m, v and b. So, this is minus small z capital Z E squared m divided by 4 pi epsilon 0 m square v square b square. One of the m will cancel and one will have a so this m will cancel with 1 m here and you get this. So, let us call this as equation 3. Now, define d, d by 2 is shown there, that is basically a length scale of length. So, that is like 4 pi epsilon 0 divided by m v square by 2. So, that is a kinetic energy. Okay. So, one can write again this in a simpler fashion. This is equal to a minus d over 2 b square, and this is nothing but a differential equation for u, a linear differential equation where the second derivative is plus the variable itself is equal to some constant for a given problem. Okay. So, a general solution for this is u equal to a cos phi plus b sin phi minus d over 2 b square, where we have used this the trial solution as well as this the specific solution. I mean the general solution is written as this for any phi. So, a and b are constants which need to be determined from the conditions that we have. And what are the conditions? The conditions are that phi is goes to 0 for r going to infinity. So, as you see that this is the phi, the angle is phi. So, if it is infinity, this phi will go to 0. And the second one is dr dt, it goes to minus v for r going to infinity. Okay. So, we are talking about v in the positive direction, that is why it is written as minus v, and that is how at very large distances we have this v, which is the velocity of the approaching particles, alpha particles. Okay. So, given these two, we can actually find out from 1 we can find out that a is equal to d over 2 b square, and from 2 we can find out b equal to m v over L, which is equal to m v over m v b, which is equal to 1 over b. Okay. So, this is say 5 and 6, which are the two unknown constants that we have determined from the boundary conditions there. So, if you put 5 and 6, we get u equal to d over 2 b square cosine of phi plus 1 over b sine phi, that is minus d by 2 b square. And then replacing or rather going back to our very own r variable. So, this is equal to 1 over b sine phi, this plus d over 2 b square, cosine phi minus 1, and that is equation 7, and that is equation of the orbit. And this is what we have been looking for, because we need to know how the alpha particle is scattered by that presence of there is a nuclear charge that is there. Of course, Rutherford did not know there is a positive charge, but he just knows that that if it has to, because the experiments say that it is deflected, most of them are undeflected, but even if there is a deflection, slight deflection, he wanted to find the trajectory of the alpha particles after collision. All right. So, this is quite simple. This is the equation of hyperbola. And it should be, I mean, in the sense that this should actually vanish to infinity unless you detect it by a detector. So, to remind ourselves that d is equal to 1 over 4 pi epsilon 0, it is a z e square over m v square over 2. Okay. So, it is basically a parameter equal to the distance of the closest approach to the nucleus when for a head on collision. So, distance of closest approach for head on collision, and head on collision would mean that B is equal to 0. Okay. So, d also refers to the distance at which the potential energy, because this is the potential energy is equal to the initial kinetic energy. Okay. Also the distance at which potential energy, which is nothing but z e square over r, which is r is equal to d here, is equal to the kinetic energy. So, initial kinetic energy, which is half m v square. Okay. So, it is easy to see, if you put d equal to r, that is what happens. Okay. Now, basically in this particular case the particle would stop because the potential energy and the kinetic energy would be same, and then it will reverse back in the incoming direction, towards the incoming direction. So, the scattering angle can be found, which is theta. So, theta can be found using theta equal to pi minus phi for r tending to infinity. So, when you capture the particle at very large distances from this gold foil that you saw, that is where that is the scattering angle, and so this cot of theta by 2, which is equal to 2b over d. Okay. So, that is the relation, and so you want to calculate this thing. Let us just redraw that picture. So, all right. So, this is basically theta, that is the scattering angle, and we want to know how many alpha particles are scattered between theta and theta plus d theta, so that we can get what is called as the scattering cross section. So, this is b and this is dB. So, the between the impact parameter b and b plus dB, what is this how many particles are scattered between that. So, we will use this want the number of particles scattered between theta and theta plus d theta, and so with particles with them between b and b plus dB. Okay. So, we use this b equal to d by 2 cot theta, and dB that becomes equal to minus d by 2 d theta by 2 sine square theta by 2. Okay, so basically d of theta by 2 sine square theta by 2. And now we can calculate the b dB, which is given by, so this b dB we have both, and that is minus d square by 8 cos of theta by 2 d theta and sine cube theta by 2. Okay, this is all algebra. You can fill in the steps, or they are all there actually. So, a b dB is equal to minus d square over 16, and we have a sine theta d theta, this divided by sine of 4 theta by 2. Okay. So, this is really proportional to the particles scattered between angle theta and theta plus d theta. So, we have a P b dB, this is equal to n theta d theta, where n theta is the number of particles, n theta d theta is the number of particles scattered between theta and theta plus d theta. They are proportional, but I am writing it as equality, and this is proportional to a sine theta d theta and divided by a sine 4 theta by 2. Without worrying about the prefactors, the scattering cross section can be obtained as d sigma d omega, scattering cross section. So, this d sigma d omega, which is equal to n theta d theta, d omega is the solid angle, and this divided by d omega, and this d omega is nothing but 2 pi sine theta d theta. So, that sine theta d theta will cancel with this. So, this is 1 by sine 4 theta by 2. There is a famous result in the sense that it is cosec 4 theta by 2, where theta is the angle that is shown, is the scattering angle. So, it is a half of that scattering angle, and this is what gives you the trajectory of this particle. Okay. And this trajectory is important because this trajectory is or rather this number of alpha particles scattered, it can be experimentally determined, and so the scattering angle dependency of that scattering cross section comes as cosec 4 theta by 2, or 1 by sine to the power 4 theta by 2. Okay. So, this is roughly what this Rutherford's model is. So, he understood that the nucleus is actually concentrated there, and of course, there are electrons also. This really does not make too much of comment about the electrons that are present in the orbiting part, or which orbit about the nucleus, but that is more succinctly told by Bohr's model. Let us just do Bohr's model. So, Bohr was more concerned with the electrons and about the stability of atoms, and if the electrons are moving around the nucleus in certain orbits, and if they are classical particles, it is easy to understand that these would lose energy and effectively would crash on to the nucleus. And if that happens, of course, nothing can exist. So, there has to be a plausible argument that there is a stability, these atoms are stable with the nucleus at the center of the atom occupying very little space, but the most massive thing in the sense that it sort of comprises of more than 99% of the atomic mass and is consisting of positively charged particles, which are protons there, and the electrons actually orbit in this around the nucleus, and these paths or these orbits or these the over which they move, the orbits over which they move around the nucleus, they have to be specified. So, Bohr came and said that look, I mean that these orbits are They do not, the electrons when they move in this orbit, they do not emit electromagnetic radiation, and these orbits are characterized by the angular momentum taking on values which are integral multiples of the Planck's constant. So, these n is equal to n 1, I mean 2, 1, 2, 3 and so on. And so, this angular momentum of these particles would really be integer multiples or integral multiples of this h, which is a Planck's constant. That seemed a little abrupt, and what could be the the reason for that. Let us try to give some explanations how he arrived at that, and why when he said that the angular momenta are quantized for these particles in those orbits, and those are the orbits which are stable orbits and they do not emit electromagnetic radiation. In fact, they can jump from one orbit to another orbit either by absorbing electromagnetic radiation, which are photons, or they can emit electromagnetic radiation and can go from a higher orbit to a lower orbit and so on. Okay. So, for these electrons the force is Z e square, where Z e is again the charge. So, Z e into E, if that helps, I will write it as Z e into E divided by 4 pi r epsilon 0 r square. R is typically the atomic radius, and this is equal to m v square by r. Okay. This is just like if you are taking I mean a stone at the end of a string, and you are wielding it in a circular orbit till you cut the string. The stone will keep rotating in that revolving in that circular orbit, and the tension actually provides the centripetal force. Here the tension, the role of the tension is played by the Coulomb repulsion between the positively charged nucleus and the electron. Okay. So, this is fine, and then of course, we have this other thing, that is mvr is equal to nh. So, if you eliminate v, so we have Z e square is equal to 4 pi epsilon 0 m v square r. This is equal to 4 pi epsilon 0 n square h cross square by m r. So, this gives r is equal to, that is the atomic radius, is equal to n square h cross square and m z e square. M is of course the mass of the electron. I mean, please do not confuse, we have done the last problem in which we said m is the mass of the alpha particles. Here of course, m is the mass of the electron. So, this is the radius, the atomic radius, and you see that very nicely this atomic radius depends on this quantum number n, where we have said n equal to 1, 2, 3 etc. So, then v becomes equal to, that is the velocity, becomes equal to nh cross by mr, which is equal to 1 over 4 pi epsilon 0, that is Z e square over nh cross, and that is 4, that is the velocity or the speed of the electrons. Okay. So, one is that the application of the angular momentum quantization, this is proportional to the n square. So, this is what we have seen here. So, r is proportional to n square, and this comes from the quantization rule. Okay. So, the atomic radius would depend upon n, where n equal to 1, 2, 3 etc. Okay. So, let us just for a moment specify it for a given problem. So, for z equal to 1, we talk about H, the hydrogen atom, that is the simplest atom that we have. So, Z equal to 1, and then if you put in I mean all these values M, E, H, etc. And one gets R is equal to 0.5 angstrom, and this is really in agreement with the atomic radii, which is of the order of 1 angstrom. Okay. Usually, so this is so how do we find the energy from this simple consideration? So, this energy is equal to, so let us talk about the potential energy first. With this radius, potential energy of the electrons. So, this is equal to minus R to infinity, and we have a Z e square by 4 pi epsilon 0 R square dr, and this is equal to minus Z e square by 4 pi epsilon 0 R, and the kinetic energy as well can be found. So, this is k is equal to half m v square, this is equal to Z e square by 4 pi epsilon 0 R. Okay. So, they are same of course, but with opposite signs. So, the total energy is equal to no, so I made a mistake somewhere. So, this is R. So, this would be 2 R, because your V is given by this. So, that is, so it is half m V square. So, one can put all these things here, and this is a 2 R here, okay, not R. Okay. And so, the total energy is equal to k plus V, this is equal to minus Z e square divided by 4 pi epsilon 0 into 2 R. And so, if you use the R that is from equation 3, so let us call this as 5, 6 and 7. So, the total energy of this hydrogen atom comes out to be E is equal to minus m z square e to the power 4 pi epsilon 0 square 2 h cross square and 1 over n square. And this is exactly what you get by solving this 3D this Schrodinger equation, that is the Coulomb potential corresponding to Schrodinger equation corresponding to the Coulomb potential. You get exactly this, and this has a value which is 13.6 with this minus sign there. So, let us remove this minus sign. So, it is minus 13.6 by n square electron volt. Okay. That is the energy. But let us sort of this quantization of the angular momentum, which is the main postulate of Bohr. What does it mean of angular momentum? All right. Okay. So, for that we start with a Bohr-Sommerfeld quantization condition. Now, this is stated, it is also called I think Wilson-Sommerfeld quantization condition, and can be kind of derived from the WKB approximations. We will probably not have too much of time to talk about that, but that is an approximate methods which gives you solutions of Schrodinger equation for linear slowly varying linear potential. So, this condition states that a PQ dQ, this is equal to NQH, okay, H or H cross does not matter. So, NQ is a quantum number which has values which are integer values, and Q is a periodic coordinate of time, which means is time periodic, which means that Q of t plus t is equal to Q of t. Okay. PQ is the corresponding momentum, and we have touched upon the generalized coordinates and generalized momenta. So, these are really the generalized coordinates and generalized momentum. So, for a particle undergoing circular motion, as is the case for an electron, so your PQ is L and Q is really theta. So, if we apply the condition, then we have a L d theta which is equal to n into h. Now, we are not writing Q, but n is a sort of quantum number which corresponds to the this coordinate. So, that tells you that L into 2 pi becomes equal to n h, and this tells you that L equal to n h over 2 pi, sorry, this is L, and this is the Bohr condition. Of course, this is mathematically consistent, there is nothing that is inconsistent about it, but we are still looking for some physical arguments and trying to understand that this condition that Bohr gave about the conservation of angular momentum or constancy of the angular momentum, which is the integral multiple of the Planck's constant, what it really means in physically what it means. So, a physical argument comes from the de Broglie principle. And the de Broglie principle states that P equal to h over lambda. We will talk about that, but just a priori telling you that this P and lambda are the momentum of the particle and wavelength of the wave. So, we will get into this quantum mechanical model of matter or quantum mechanical interpretation of matter. Matter can exhibit both wave and particle nature if they behave, or rather they display both these features of that of particle and that of a wave. Then there has to be a correspondence between, because it is the same system. In some experiments it shows as particle, in some system it shows as wave. So, the particle aspect is shown by its momentum, because there is a mass and there is a velocity and so on, and the wave aspect is shown by its wavelength, and this is a relation that connects the momentum of the particle and wavelength of the wave. So, if you write this the MVR, which is the angular momentum, so this is nothing but PR, this is equal to NH over 2 pi. As we said that H and H cross are same. Initially Bohr's postulate was simply NH, but then we just got it here as NH over 2 pi. Okay, it is just a division of 2 pi, it will not matter at least physically anything. So, if you apply P equal to H over lambda, then this gives you HR over lambda, this is equal to NH over 2 pi, and the H will cancel, and that gives 2 pi R equal to n lambda. Now, this is an important thing and can be physically interpreted. This tells you that the wavelength of the particle should have integer number, or rather an orbit of the particle should accommodate integer number of wavelengths. It cannot happen that it has the n is not a number. Okay. So, let me give you an example. So, this is a sort of orbit, okay, badly drawn, but you understand that. So, this and sort of so one. So, it is just showing that, so this is the orbit, and so I am just showing it a little off that because you need to sort of show that there is one complete orbit. So, this n equal to 1. Okay. So, this one corresponds to, say for example, so there are kind of 2 orbits that are there. So, n equal to 2, and another orbit should have this is probably the most so let us so this is n equal to 3 and so on. Maybe I have drawn not very well, but what I want to say is that this accommodates the orbit is such that it accommodates integer number of wavelengths of the particle. And where is this condition coming from? This condition is coming from the Bohr's postulate, which is about the conservation, or rather the quantization of the angular momentum. And so, the quantization of the angular momentum means that a particle with its with its equivalent wave description would have wavelengths, the orbit of the wave would accommodate exactly integer number of wavelengths, and that, so they should be consistent, and that talks about the stability of the orbit. So, it cannot happen that they do not join, I mean, say I sort of draw another one where you have this and so on, that cannot be true. Okay. So, it does not have this integer number of wavelengths, whereas the other ones have. Okay. So, this is something that will physically connect the reason that for the stability of these atoms, Bohr had proposed this postulate of the quantization of the angular momentum. So, we will stop here for today and we will continue next class.